Welcome to InjectFlow's Math Series, Module 1, Lesson 9, Logical Connectors. We'll explore the building blocks of logic, and, or, and not. In logic, we start with simple statements, like, it is raining, or, I have an umbrella. These are our basic building blocks. But how do we combine these simple ideas to form more complex ones? We use logical connectors. The three most fundamental are AND, represented by this symbol, OR, represented by this one, and NOT, represented by this symbol. Let's start with the AND connector. Its symbol is this upward-pointing wedge, and its formal name is conjunction. Let's take two simple statements. We'll call them P and Q. Let P be the statement, it is raining. And let Q be the statement, it is cold. We can combine them using the AND connector to form the new statement P and Q. We would read this as, it is raining and it is cold. But when is this new combined statement true? We can map this out using a truth table. The table shows every possible combination of truth values for P and Q. If P is true and Q is true, then P and Q is true. If P is true but Q is false, P and Q is false. If P is false but Q is true, P and Q is still false. And if both P and Q are false, P and Q is false. The key insight for the AND connector is this. The combined statement is only true if both parts are true. Next, let's look at the OR connector. Its symbol is a downward pointing wedge, and its formal name is disjunction. Let's use new statements. P, I study hard. Q, I get lucky. We can combine them to form P or Q. We read this as, I study hard or I get lucky. So when is this statement true? Let's build its truth table. We have our headers, P, Q, and P or Q. If P is true and Q is true, then P or Q is true. If P is true but Q is false, P or Q is still true. If P is false but Q is true, P or Q is also true. It's only when both P and Q are false that P or Q is false. The key insight for the OR connector is that the combined statement is true if at least one of the parts is true. Finally, we have the NOT connector. Its symbol looks like this, and its formal name is negation. Unlike AND and OR, negation doesn't combine two statements. It operates on just one. Let's take the statement P. The sky is blue. Applying the NOT connector gives us not P. We read this as, the sky is not blue. The truth table for NOT is much simpler. We just have P and not P. If P is true, then not P is false. And if P is false, then not P is true. The key insight is simple. Not just flips the truth value. The real power comes from combining connectors. We can use these simple rules to build much more complex statements. Let's define two statements. P, it is sunny. Q, it is warm. Now, what does this complex statement mean? Not P and Q.
Let's break it down. First, not P means it is not sunny. Second, Q just means it is warm. So, not P and Q combines these with an and, giving us it is not sunny and it is warm. If these symbols look familiar, they should. There is a deep connection to set theory. In logic, we have our three connectors. And in set theory, we have three very similar operations. The logical AND corresponds directly to the set intersection. The logical OR corresponds to the set union. And the logical NOT corresponds to the set complement. This isn't a coincidence. They are two ways of describing the same underlying structure. This structure isn't just abstract, it's physical. This is the foundation of logic in computing. These connectors are built into physical circuits called logic gates. For example, this is a diagram of an AND gate. It takes two electrical inputs, which we can call P and Q, and produces a single output, P and Q. In this system, a truth value is represented by a voltage. A high voltage signal means true. A low voltage signal means false. This simple AND gate, and combined with billions of others, is what allows your computer processor to perform complex calculations. Let's summarize. We learned three logical connectors. The AND connector, P and Q, is true only when both P and Q are true. The OR connector, P or Q, is true when at least one of them is true. And the NOT connector, not P, simply flips the truth value of P. These three simple tools are the fundamental building blocks of all logical reasoning. You've completed the lesson on logical connectors, the very chemistry of logic. Next, we'll explore one of the most important structures in logic, conditional statements, also known as if-then.